Hi everyone, in this video I'm going to review the in-class activity covering epistasis. The first thing that's the most important part of answering these questions is understanding how to read and analyze the pathway that's given. So here's the example. We're looking at sweet peas and the synthesis of purple anthocyanin pigment in petals, which is controlled by two genes, B and D. These genes are known to assort independently, and here's the pathway. So again, being able to read and understand the pathway is super important. So first things first is you start with your white intermediate. Then next, if gene B enzyme is working, then you're able to move on to the next step, which is the blue intermediate. If the gene D enzyme is working, then you'll get the final color of purple, or the anthocyanin. However, the anthocyanin purple color is only going to be produced when both B and D are working. So this is super important to note, is both have to be working, not just one or the other, but both enzymes. Okay, the next part is, again, we're starting with the white intermediate. If gene B enzyme is not working, you need to jump back to the previous color because the enzyme cannot keep going. You cannot keep going in the pathway. You have to jump back to the previous color, and that is what you would get. So if gene B is not working, you would get a white intermediate. Similarly, if your gene B enzyme is working, you would move on to the blue intermediate. However, if gene D enzyme is not working, then again, you would jump back to the previous color. So if gene D is not working, you would get a blue intermediate. So that's kind of how to read the pathway and figure out like what is working. So let's look at the questions. So consider a plant that is specifically mutated for the B gene and unable to catalyze the first reaction. What color petals would you see? So there's a mutation here in this B enzyme, so that means that this one does not work, so put an X, and then again we're going to jump back to the previous color, which would make this individual white. Again, because B has a mutation, it can't move on to the next step to produce that blue color. Okay, and then write the genotype for this plant, including both the mutation for the gene B and the normal alleles for gene D. So when we're thinking of the genotypes, because this is recessive epistasis, we would say that B/dash would be working because you have one good copy of the allele, so it's haplosufficient. One is good enough for it to work. But only if you'd have little b or homozygous recessive, that's when it would not. Okay, and then similarly to gene D, big D/dash. So again, you have one good copy of that D allele would result in the enzyme working, but a homozygous recessive individual would result in it not working. So when we're looking at what the genotype for a white petal individual would have, again, they have a mutation for the B gene and normal alleles for D. So a mutation in B would look like little b, and then a dot because they're two different genes, and then big D, because the question says normal alleles, while big D/dash, because while this technically could result in a working phenotype because you have one working copy of the D enzyme, because this question says it has normal alleles, we're going to assume that means they have homozygous dominant genotype, because normal would have both normal alleles. They wouldn't have a defective copy. So that would be the genotype, and this would be plant 1. And again, this little b means that it's unable to catalyze the B gene enzyme. Okay, next question is the same thing, it's just the opposite gene. So we're looking at the D gene, and we are unable to catalyze the second reaction. So what color petals would you see? So going to this enzyme right here, so we are unable to catalyze it, so put an X over top of it, and then jump back a space, and that would give you a blue color. Again, remember, if there is a mutation in this D enzyme, remember B would work, so you'd get that blue intermediate. You'd go to the gene D enzyme, jump back a space because it cannot keep going forward because the enzyme does not work. So that's why you would get that blue color. Okay, and then when you're looking at the genotype for this plant, include the mutation for gene D and the normal alleles for gene B. So a normal allele, the normal alleles for gene B would be big B, homozygous dominant, dot, and then there's a mutation for gene D, so that would be represented as little d, or homozygous recessive. And this is plant number 2. Remember, this represents a functional copy that's working, can be catalyzed. This represents a non-functional copy, cannot catalyze it, which means it does not work, does not produce the next color. Okay, question number 3, you complete an experiment crossing the plants described in question 1 with the plant described in question number 2. So just the two individuals that we just found out. Write the genotype for F1 plant from the cross between these two lines. So again, we are just taking this individual right here, and we are crossing it with the individual right here. And make sure, don't forget to put X to show that you're crossing the two. And then if you would do a regular Punnett square, you would get one big B, one little b, so heterozygous for the B gene, and heterozygous for the D gene. And we got that by little b times big B, little b, and big D, little d, and big D, little d. So again, that would just be doing like your normal like separate 2x2s. So if you did big B times little b, and then big D, little d. And that's how you would get all heterozygous individuals. Okay. And then the next question, predict the phenotypes of the F1 plant from the cross between these two lines. So here's, again, your answer right here, heterozygous for both genes. You have one functional copy of the B gene and one functional copy of the D gene, so that would lead to purple. Because you have, go back up to my pathway, you have one good copy of B, which means you get to move on to the blue intermediate, and you have one good copy of the D, which means you get to move on to that purple color. Okay, and then the last question, if you allowed this F1 plant to self-fertilize, what would you expect to see? So when they're talking about this, you're looking at the heterozygous individual, so you'd essentially be doing big B, little b, times big B, little b, dot, big D. So again, selfing is just you're taking the same genotype you got and crossing it times itself, or the exact same genotype. So I'll show you really quickly what this looks like in a 16 box Punnett square. So here's what it looks like. You have one of each combination. So two of the the working copies, or big B little, or big B big D, big B little d, big D, and then a little b little d. And then same thing, looking here on this side, you have two bigs, a big and a little, big, a little and a big, and then two littles. So this is the 16 box Punnett square. This is, you can draw this out. I don't necessarily recommend it personally. I like to just understand and be able to memorize and identify the 9 to 3 to 3 to 1 ratio. I think that one is a lot easier to be able to look at and identify. So here, down here, the genotype ratio, you have your 9 that are, you have at least one big copy of, functional copy of capital B, and one functional copy or a capital D. So that's represented by all the pink. And then you have 3 that are represented by one functional copy of the B gene, but you have a mutated copy of the D gene represented by little d slash little d. So that is in orange. And then you have blue, which is all, or excuse me, green, which is also represented by that other 3. You have a non-functional copy of the B gene. However, you have one good functional copy of the D gene, so that D slash dash can be represented by big D, little d, or heterozygous individual, or a homozygous dominant, big D, big D. And then lastly, here in your blue color, you have one that has a mutated copy of both genes. So they have a non-functional copy of the B gene and the D gene. So again, I recommend understanding and being able to recognize and write out this ratio, the 9 to 3 to 3 to 1. So I think of it as dihybrid. So like dihybrid heterozygous. So again, when you're crossing a heterozygous individual times a heterozygous individual for 2 gene traits, if you're able to understand, recognize, and honestly memorize the 9 to 3 to 3 to 1 ratio, you should be good to go. So again, 9, just remember that 9 individuals, 9/16 of the individuals will have at least one good copy of both the B and the D enzyme. So one good copy of both. Let me get rid of this so it's a little less confusing. And then 3 of them will have one functional good copy of the B. However, they will not have a good functional copy of the D enzyme. And then going back, 3, they will not, 3 of the individuals will not have a good B, but they will have a good D gene. And then lastly, the 1/16, they're not going to have a good functional copy of either the B or the D enzyme. So kind of going back to my pathway up here, let me show you back here. So if we're looking at the pathway up here, and we're kind of understanding how this all works, so you have some that are good to go all the way through, 9 of them. You have 3 of them that have a good B enzyme, so they can get to this blue color. However, they have a non-working D enzyme. So again, jumping back a space. And then you have some individuals that have a bad B enzyme. So again, jumping back a space. However, they have a good D enzyme. But even though they have a good D enzyme, it doesn't really matter because they can't get past the blue. They can't get past this spot because the B enzyme does not work. So again, B and D work together. So gene B influences gene D. And then lastly, the last option is there's no good enzymes, no good alleles at all. So there's no functional copies of the gene B or the gene D enzyme. Okay, so then when we're looking at colors, you'll see that you'll have 9 purple, because again, you're able to make it all the way through the pathway because you have one good B and you have one good D enzyme. And then you have 3 individuals that have at least one good copy of B. However, they don't have a good copy of D. So that means if you look at your pathway, you got to jump back a space. So again, good B, not a good D. So you get stuck here at your blue intermediate. And then the other 3 would have, you would not have a good B enzyme, but you would have a good D enzyme. And that, again, you jump back a space, and that would give you white. And then the last option is you have neither of your genes are good. So again, if you can't get past this gene B enzyme to make the blue intermediate, you gotta jump back to your white. And that is how you get your 9 to 3 to 3 to 1 genotype, but you have your 9 to 3 to 4 phenotype. So again, 9 purple, 3 that are blue, but these 2 right here, these would be your white. Because again, if you don't have a functional B enzyme gene, you can't keep going further into the pathway. Okay, I hope that was a good, helpful explanation. My recommendation is to be able to memorize and understand the 9 to 3 to 3 to 1 genotype. And if you're good to go with that, and you can kind of remember what the 9, what the 3, what the other 3, and what the 1 stand for, and what those genotypes are, you'll easily be able to figure out what the phenotypes are. Don't forget, when you're writing out both the genotypes and the phenotypes, to label. So make sure you put your 9 next to your correct genotypes. The same goes for phenotype. If you're just writing the colors and you write 9 to 3 to 4, make sure to label them like they are right here. So the person grading it knows which color is represented by the 9, which is represented by the 3, and which is represented by the 4. I hope you enjoyed this video. I hope you found it helpful, and thank you for watching.